There are things that happen beyond the atmosphere that never make it into the press release. Not because they aren't real, because they are. On April 12, 2026, the Artemis II crew crossed the Van Allen radiation belts. Two massive rings of charged particles trapped by Earth's magnetic field, spiraling at energies capable of destroying unshielded electronics in minutes and delivering lethal doses of ionizing radiation to unprotected biological tissue.
Houston,
The official
trajectory is
broadcast
nominal.
showed
We
a
are
clean
passing over the
trajectory,
Terminator now.
a smooth
All
arc,
systems holding steady.
calm voices confirming system status. What the broadcast did not show was the data. The outer Van Allen belt extends roughly 58,000 kilometers from Earth's surface. At peak solar activity, which we are in right now during solar cycle 25's maximum, proton flux inside that belt can spike by orders of magnitude within hours. No warning, no pattern, just the sun deciding in one violent exhalation of magnetized plasma to flood the path between here and the moon with enough radiation to rewrite the cellular structure of everything in its way. Artemis II flew through that. They flew through a corridor where the difference between mission success and catastrophic crew exposure is measured not in miles, but in minutes, sometimes in seconds. Depending on solar wind conditions that no agency on Earth can fully predict more than 48 hours in advance. And the broadcast cut to a congratulatory graphic. This is not speculation. This is the physics of the heliosphere. The sun is not a stable lamp in the sky. It is a thermonuclear reactor with a surface temperature of 5,500 degrees Celsius and a corona that reaches over 2 million degrees. A temperature differential so paradoxical that astrophysics still has no complete explanation for it. It breathes. It erupts. It sends walls of magnetized particles across 150 million kilometers of space at speeds exceeding 700 kilometers per second. And when those walls arrive, they do not knock. They enter. Every human being aboard Artemis II flew through the edge of that storm. What NASA showed you was the rocket. What NASA did not show you was what the instruments were reading while the rocket flew. That silence, that particular deliberate silence, is what this documentary is about. Before there was Earth, before there was a moon to orbit, before the first grain of silicate rock condensed out of the swirling disk of gas and dust that would become this solar system, there was the field. The magnetic field. It does not make a sound. It has no color. You cannot touch it or taste it or see it with any instrument your naked eye could ever interpret directly. And yet, without it, you would not exist. Nothing on this planet would exist. Not the oceans, not the atmosphere, not the delicate, improbable chemistry that spent 4 billion years assembling itself into something capable of wondering about its own origins. The magnetic field is the reason life happened here, and as far as we can confirm, nowhere else in this solar system. It is generated roughly 2,900 kilometers beneath your feet, inside a liquid iron outer core spinning at temperatures exceeding 5,000 degrees Celsius, nearly as hot as the visible surface of the sun itself. The differential rotation of that molten iron, combined with Earth's own spin, creates electrical currents on a planetary scale. Those currents generate the field. The field extends outward into space, deforming and stretching under the constant pressure of the solar wind into a teardrop shape. Rounded on the sun-facing side, stretched into a tail that extends hundreds of thousands of kilometers in the opposite direction, like a flag perpetually blown by an invisible hurricane. That structure is called the magnetosphere, and the Artemis II crew had to leave it. Think about what that means for a moment. Not as a technical fact, as a human reality. Every ancestor you have ever had lived and died inside that field. Every war, every civilization, every act of love or cruelty or creation in the entire recorded history of the human species, every single moment of it happened inside the protective envelope of that magnetic architecture. When ancient sailors navigated by the stars, they were inside it. When the first hominids looked up from the African savanna and felt something like wonder for the first time, they were inside it. When the Apollo astronauts became the first human beings to leave it, briefly, partially, incompletely, they stepped into a realm that our biology was never designed to survive in for long. The Van Allen belts are the first warning. They are the magnetosphere's most concentrated expression of danger. Two donut-shaped zones where the field traps high-energy particles from the sun and from cosmic sources far beyond this solar system, forcing them into tight spiraling paths along magnetic field lines. The inner belt begins roughly 1,000 kilometers above the surface and is dominated by high-energy protons, some accelerated to a significant fraction of the speed of light. The outer belt, beginning at around 13,000 kilometers and extending to roughly 58,000, is primarily composed of high-energy electrons, particles so small they are almost conceptually abstract, yet so energetic they can penetrate metal shielding, induce currents in electronics, and pass directly through human tissue, leaving ionization trails in their wake like invisible bullets fired through everything you are. Ionizing radiation does not feel like anything when it enters you. That is perhaps the most unsettling truth of deep space. The most dangerous environment a human being can occupy announces itself with complete silence. No heat, no pressure, no pain. The particles move through your skin, through your organs, through the nucleus of your cells. And they leave damage that your body sometimes repairs and sometimes does not. The damage they leave in DNA is not always immediate. Sometimes it expresses itself years later as a mutation in a cell that was struck once, briefly, on a 4-day journey around the moon in 2026, and then spent the next decade quietly replicating that error. This is what radiation exposure in the Van Allen belts means in biological terms. Not a burn, not a shock. A whisper in the language of chemistry, spoken directly into the architecture of your genome. The Apollo program flew through the belts quickly, on trajectories specifically calculated to minimize exposure time, threading through the thinner regions, spending as little as 30 minutes in the most intense zones. Even so, several Apollo astronauts reported seeing light flashes with their eyes closed. Cosmic ray particles passing directly through their retinas and optic nerves, producing phosphene effects with no source of light. They were seeing radiation. They were watching high-energy particles write themselves directly onto their visual cortex, bypassing the eye entirely. That phenomenon was documented, studied, filed. And then, for decades, human beings stopped going far enough from Earth for it to matter. The International Space Station orbits at roughly 400 kilometers altitude, well below the inner Van Allen belt, still inside the magnetosphere's protective embrace. Every astronaut who has lived aboard the ISS for 6 months or a year was never truly outside. They were still, in the most fundamental physical sense, at home. Exposed to elevated radiation compared to the surface, yes, but not to the full, unmediated fury of the heliosphere. Artemis II changed that equation. The trajectory of Artemis II was a hybrid mission, a crude lunar flyby, not a landing, but a journey that took the Orion capsule and its 4 crew members on a free return path around the moon that at its farthest point placed them approximately 10,000 kilometers beyond the lunar surface. That is roughly 384,000 kilometers from Earth. That is outside the magnetosphere. That is in the open heliosphere, exposed to whatever the sun decides to do. And the sun, in April 2026, was not being quiet. Solar Cycle 25 had been tracking more intensely than the original NASA prediction suggested. The Solar Dynamics Observatory, the Parker's Solar Probe, and the European Space Agency's Solar Orbiter had all been documenting a pattern of escalating activity. Coronal mass ejections of increasing frequency, sunspot counts near historic highs, X-class solar flares erupting from active regions on the solar disk, with the kind of regularity that makes mission planners either very brave or very uncomfortable. A coronal mass ejection is not simply a burst of light. It is a coherent structure, a bubble of magnetized plasma. Billions of tons of charged particles expelled from the sun's corona at velocities ranging from a few hundred to over 3,000 kilometers per second. When a CME impacts Earth's magnetosphere, the results are visible even to the naked eye. Auroras painting the sky in curtains of green and red, electromagnetic interference disrupting communications and power grids. The 1989 Quebec blackout, when a geomagnetic storm knocked out power for 6 million people for 9 hours, was caused by a CME. The Carrington event of 1859, the most powerful geomagnetic storm ever recorded, would today, if it struck with the same intensity, be capable of disabling satellite systems and terrestrial power infrastructure on a global scale. Those were events experienced from inside the magnetosphere, events where Earth's own field, strained and compressed and partially overwhelmed, still absorbed much of the incoming energy. Outside the magnetosphere, there is no such buffer. Outside the magnetosphere, a CME does not interact with a protective field before it reaches you. It reaches you directly. It is the difference between standing behind a thick stone wall while a hurricane passes and standing in the open field where the hurricane began. The Orion capsule's shielding was designed for elevated radiation environments. Water walls, polyethylene panels, the positioning of equipment as additional mass between the crew and the highest radiation directions. These are real, engineered solutions. But they are solutions to a statistical problem, not an absolute one. They reduce exposure. They do not eliminate it. They shift the probability curve toward survivability. They do not remove the crew from the domain of risk, and on at least 2 separate occasions during the Artemis II transit, solar particle events were detected by heliospheric monitoring instruments. Modest events by the sun standards, but events nonetheless. Energetic proton fluxes elevated above background. The kind of readings that, during an EVA on a lunar surface or on a trajectory without adequate warning time, can cross the threshold from manageable exposure into acute radiation syndrome territory within hours. The broadcast did not mention this. The broadcast showed windows, showed the curvature of the Earth, showed 4 people smiling in a capsule that cost more to build than the GDP of several small nations, floating in the impossible beauty of cislunar space. And somewhere, in a room where mission controllers watch instrument feeds that never appear on the public stream, the dosimeters were telling a different story. Not a catastrophic story. The crew survived. They completed the mission. They splashed down in the Pacific Ocean and emerged from the capsule and smiled for the cameras. But survival is not the same as safety. And the distance between those 2 words is where the most important conversations about human spaceflight have always lived. and where they have almost always been conducted in private. The question this documentary is asking is not whether NASA lied. It is asking something more precise and more troubling. What does it mean to send human beings into an environment that is fundamentally incompatible with human biology, equipped with instruments sophisticated enough to measure exactly how dangerous that incompatibility is, and then curate what those instruments say before the public sees it? What does it mean to stand at the edge of the abyss and describe it to the people watching at home as a view? There is a frequency the sun speaks in that no human ear can detect. It is not a metaphor. The sun produces radio waves, X-rays, ultraviolet radiation, and extreme ultraviolet pulses that arrive at Earth's upper atmosphere and are absorbed before they ever reach the ground. You have lived your entire life bathed in energies your senses were never built to perceive, filtered by layers of atmosphere and magnetism so effective that the surface of this planet feels, to your nervous system, like a quiet room, a sanctuary, a place where the universe has agreed, for the moment, to leave you alone. That agreement ends at roughly 100 kilometers altitude. Above that threshold, the boundary physicists call the Kármán line the formal edge of space. The filters begin to thin. The atmosphere becomes too sparse to absorb. The magnetic field becomes the last remaining structure standing between biological tissue and the full electromagnetic vocabulary of a star. And the further you travel from Earth, the more of that vocabulary you begin to hear, not with your ears, but with your cells. The Artemis II crew, at their farthest point from Earth, was listening to all of it. What they were immersed in has a name that sounds almost peaceful. The interplanetary medium. It is the space between planets, not empty, not silent, but threaded with the solar wind, a continuous stream of electrons and protons exhaled from the sun's corona at an average velocity of 400 to 800 kilometers per second. The solar wind is not a wind in any familiar sense. It does not push against you. It passes through you. It is a plasma, a fourth state of matter, distinct from solid, liquid, and gas. And it fills the entire volume of the solar system out to a boundary roughly 120 astronomical units from the sun, where it finally loses enough energy to be overtaken by the interstellar medium beyond. That boundary is called the heliopause. Beyond it is true interstellar space. The Voyager probes crossed it. Our farthest human-made objects, launched in 1977, carrying golden records with the sounds of Earth, now drifting through a region of space so remote that the signal traveling at the speed of light takes more than 22 hours to reach us. They crossed that boundary and found something unexpected. The interstellar medium was pushing back. There is pressure out there beyond the sun's reach. The accumulated exhalation of other stars, other stellar winds, the background radiation of the galaxy itself pressing inward against the bubble our sun has carved into the cosmos. We live inside a bubble. The heliosphere is a bubble, and like all bubbles, it has a wall, and beyond that wall is an ocean we have barely touched. But the Artemis II crew did not need to reach the heliopause to be vulnerable. They only needed to be 384,000 kilometers from home. They only needed to be outside the magnetosphere. Because in that space, in that interplanetary medium between the Earth and Moon, the solar wind arrives unmediated, and with it comes something that deserves far more attention than it typically receives in public discussions of spaceflight: a galactic cosmic rays. Galactic cosmic rays are among the most energetic particles in the known universe. They are not produced by the sun. They come from outside the solar system entirely, from supernova explosions, from neutron star mergers, from the relativistic jets of active galactic nuclei thousands of light years away. They are atomic nuclei, hydrogen nuclei, helium nuclei, iron nuclei, stripped of their electrons and accelerated to velocities approaching the speed of light by the most violent processes the universe knows how to produce. When an iron nucleus traveling at 99.9% the speed of light enters a human body, it does not stop cleanly. It tears a column of ionization through tissue, disrupting cellular structures along a track that can be microns wide but biologically catastrophic in its implications. These tracks have been studied in cell cultures, in animal models, in computational simulations. They produce a particular kind of DNA damage. Clustered lesions, multiple breaks in close proximity, that the cell's repair machinery handles with significantly less efficiency than damage from more familiar radiation sources. The central nervous system is especially vulnerable. This is a finding that has been accumulating in the scientific literature for years, drawn from animal studies conducted specifically to understand the risks of deep space travel. Mice exposed to simulated galactic cosmic ray environments show measurable changes in cognitive function, reduced performance in spatial memory tasks, signs of anxiety behavior, evidence of neuroinflammation. The hippocampus, the brain region most associated with memory formation and spatial navigation, shows structural changes at the cellular level. Dendritic branching, the physical architecture of how neurons connect to each other, is altered. These are mice. The translation to human biology is not direct or certain, but it is not zero. And the Artemis II crew were not mice in a simulation. They were 4 human beings with hippocampi and prefrontal cortices and the full, irreducible complexity of primate neurology, traveling through an environment where galactic cosmic rays arrive continuously, from every direction simultaneously, at a flux that cannot be meaningfully shielded against with any mass of material that a crude spacecraft can practically carry. There is no known shielding solution for galactic cosmic rays. This is not a gap in current technology. It is a fundamental physical constraint. High-energy cosmic ray nuclei interact with shielding material and produce secondary radiation, a shower of particles generated by the collision itself, sometimes more biologically damaging than the primary particle would have been. More mass does not always mean more protection. In some energy ranges, thicker shielding makes the situation worse. The problem is not engineering, it is physics. And physics, unlike a press release, cannot be revised after the fact. This means that every crewed mission beyond low Earth orbit, every mission to the Moon, every proposed mission to Mars, every vision of human expansion into the solar system, carries with it an irreducible neurological cost that begins accumulating from the moment the spacecraft leaves the magnetosphere and does not stop until it returns. A 6-month transit to Mars, each way, would expose the crew to galactic cosmic ray doses far beyond anything experienced during the Apollo missions or the Artemis program. The total integrated dose over a round trip, combined with solar particle event exposure, would place the mission firmly in a risk category that, by any terrestrial occupational radiation standard, would be classified as unacceptable. The limits that govern radiation workers in nuclear facilities, in hospitals, in industrial environments, those limits exist because decades of epidemiological data have established the relationship between dose and cancer risk with sufficient precision to draw lines. A Mars mission would cross those lines, not accidentally, deliberately, with full knowledge, because there is currently no other way. And so the question that lives quietly inside every public announcement of human deep space exploration ambitions is this: what are we actually asking people to accept? And who gets to decide whether that acceptance is informed? The Artemis II crew were volunteers. They trained for years. They understood, at some level of professional abstraction, the risks they were taking. They signed documents. They received briefings. They are among the most thoroughly prepared human beings ever to sit atop a rocket. But preparation is not the same as comprehension. Not because the crew were incapable of understanding, they were extraordinarily capable, but because some risks exist at a scale that resists full internalization. The long-term neurological effects of galactic cosmic ray exposure may not express themselves for years, possibly decades. A cognitive change that begins in the hippocampus during 4 days in cislunar space in April 2026 might not become clinically apparent until 2035. It might never become clinically apparent at all, or it might. And the uncertainty itself, the radical, irreducible uncertainty about what the body is quietly doing with the damage it accumulates in silence, is something the broadcast graphics and the congratulatory music and the carefully framed camera angles through the Orion window simply do not have the capacity to convey. The broadcast showed you a triumph, and triumph it was. Genuinely, undeniably. The Artemis II mission was a staggering technical achievement. The Orion capsule, the space launch system, the navigation, the life support, the re-entry, all of it represented thousands of engineers and scientists and technicians pouring years of their lives into something real and extraordinary. But triumph and danger are not opposites. They are not mutually exclusive. The most profound achievements in human history have almost always been purchased at costs that were not fully visible at the time they were being paid. The explorers who first crossed oceans in wooden ships were triumphing over geography and ignorance and their own fear. And they were also dying of scurvy, of infection, of storms, of the quiet accumulation of biological damage that the age did not yet have the vocabulary to name. We have better vocabulary now. We have dosimeters and particle detectors and cellular biology and neuroimaging. We have the instruments to name what is happening. We simply do not always choose to speak those names in the same breath as the triumphant ones. And that choice, that particular, recurring, deeply human choice to narrate the light and leave the shadow unnamed, is not unique to space agencies. It is not a conspiracy. It is something older and more fundamental than that. It is the same instinct that causes a species standing at the edge of a new frontier to tell itself the story it needs to hear in order to take the next step. We have always done this. We have always looked at the darkness ahead and described it, for the benefit of those watching, as the beginning of the light. The question is not whether that instinct is wrong. The question is what we lose when we indulge it. What precision we surrender. What preparation we forego. What conversations we fail to have with the people who will one day be asked to go farther than Artemis II went. Farther than the moon, into the deep interplanetary dark, where the cosmic ray flux is higher, where the solar particle event warning times are shorter, where the distance from Earth means that no rescue is physically possible, and where the irreversible biological clock of radiation exposure ticks without pause for months at a time. Those people deserve more than triumph narratives. They deserve the full vocabulary of the risk they are being asked to carry. Not to discourage them, but because the full vocabulary, spoken clearly, is the only foundation on which genuinely informed courage can be built. Courage that does not know what it is facing is not courage. It is momentum. And momentum, in space, will eventually carry you somewhere you cannot come back from. Every atom of calcium in your bones was forged inside a star that no longer exists. Not metaphorically, not as a poetic approximation of a more complex truth. Literally, with the full weight of nuclear physics behind the statement. The calcium in your skeletal structure, the iron in your hemoglobin, the oxygen in every breath you draw, the carbon that forms the backbone of every organic molecule in every cell of your body. None of it was produced on Earth. None of it was produced in this solar system. All of it was synthesized in the nuclear furnaces of stars that lived and died before the sun was born, and dispersed into the interstellar medium by the violence of their deaths, and gathered by gravity over millions of years into the cloud of gas and dust that collapsed 4.6 billion years ago. Into this solar system, this planet, this ocean, this chemistry, this you. You are, in the most literal physical sense, made of dead stars. And when the Artemis II crew left the magnetosphere and entered the interplanetary medium, they were returning, briefly, partially, in a pressurized aluminum and carbon fiber shell traveling at kilometers per second, to the kind of environment in which those atoms were originally dispersed. They were moving through the same interplanetary medium that the solar wind has always filled, the same flux of galactic cosmic rays that has always threaded through this solar system from the remains of stellar explosions in the galaxy's distant past. They were, in a sense that is simultaneously poetic and physically precise, moving through the medium of their own origin. There is something in that fact that resists easy assimilation. The human mind is not well calibrated for the timescales involved. 1 billion years is a number you can write, can read, can perform arithmetic on. But you cannot feel it. You cannot hold it in the same cognitive space where you hold the feeling of a year passing, of a decade, of a lifetime. The gulf between the temporal scales of human experience and the temporal scales of cosmic process is not just large, it is of a different categorical order. The same kind of difference that exists between counting to 1,000 and counting to a number so large that all the atoms in the observable universe would be insufficient to represent it in decimal notation. And yet, the cosmos operates on those scales indifferently, continuously, without reference to the timescales of the organisms that have recently developed the capacity to notice it. Stars are born and live and die on timescales of millions to billions of years. Galaxies collide and merge on timescales of billions of years. The universe itself, by current measurement, is approximately 13.8 billion years old. A number that places the entirety of recorded human history, roughly 10,000 years, at less than 1/1,000,000th of cosmic time. If the age of the universe were compressed into a single calendar year, all of human civilization would occupy the final fraction of the final second of December 31st. We are, cosmically speaking, brand new. We are an experiment so recent that the universe has barely had time to notice we are here. And yet, here we are, sending metal capsules into the interplanetary medium, trying to understand the environment that made us, equipped with instruments sensitive enough to detect individual particles from supernova remnants thousands of light years away. Aware enough to know what those particles are and where they came from, and still not entirely sure what they are doing to us at the cellular level during the days we spend immersed in their flux. This is the paradox at the heart of human space exploration. We are sophisticated enough to go, and not yet sophisticated enough to fully understand what going costs. We have built rockets that can carry human beings to the moon and back with extraordinary reliability. We have not yet built a complete picture of what those human beings carry back inside them, in their DNA, in their neurological architecture, in the microbiome shifts, and the cardiovascular remodeling, and the subtle, persistent alterations to the systems that keep a biological organism functional over the decades, following a mission that lasted only days. The data exists in fragments, scattered across the peer-reviewed literature of space medicine. It exists in the longitudinal health records of the astronaut corps, in the follow-up studies of Apollo veterans, in the animal research conducted under simulated deep space radiation conditions. And when you assemble those fragments, when you read across the literature with the attention it deserves, without the filter of institutional communication strategy, without the editorial choices that determine which findings appear in a press release and which findings appear only in the supplementary materials of a journal article that the public will never read, a portrait emerges that is considerably more ambiguous than the one offered by mission highlight reels. The Apollo astronauts, as a cohort, have shown elevated rates of cardiovascular mortality compared to age-matched controls and compared to astronauts who flew only in low Earth orbit. A study published in Scientific Reports in 2016 found that Apollo lunar astronauts died from cardiovascular disease at a rate 4 to 5 times higher than astronauts who had not left the magnetosphere. The sample size was small. Only 7 of the 24 lunar astronauts had died at the time of the analysis, limiting statistical power. The confounders are real. These were men of a specific generation, with specific exposure histories, who lived the rest of their lives in specific ways that may have contributed to their cardiovascular outcomes independently of their spaceflight experience. But the signal is there, in the data, elevated, waiting to be confirmed or refuted by larger data sets that, given the pace of deep space human exploration, will take decades to accumulate. The proposed mechanism connects directly to the radiation environment they pass through. Galactic cosmic rays and solar particle events produce endothelial damage to the cells lining the interior of blood vessels. The endothelium is not merely structural. It is a metabolically active tissue, producing signaling molecules that regulate vascular tone, inhibit clotting, mediate inflammation. Radiation-induced endothelial dysfunction produces an inflammatory state in the vessel wall that accelerates atherosclerosis. The progressive narrowing of arteries by plaques of oxidized lipid and inflammatory cells that, over decades, produces the cardiovascular disease that kills more human beings than any other single cause on this planet. A 4-day mission through the Van Allen belts and cislunar space in the 1960s and 70s may have initiated a process in those 24 men's cardiovascular systems that expressed itself not in the weeks following the mission, not in the years of post-flight medical monitoring, but in the decades of subsequent life, when the biological consequences of that brief radiation exposure intersected with the ordinary accumulation of cardiovascular risk that comes with aging. This is radiation's cruelest characteristic. It is a delayed creditor. It does not collect immediately. It waits. It waits while you return to Earth and give your press conference and write your memoir and give your speeches to school children about the wonder of space. It waits while you retire from the astronaut corps and build your civilian life and watch your children grow. And then, in the fullness of time, in the 3rd and 4th decades after the mission, when the cumulative cellular damage has had sufficient time to propagate through the biological systems it disrupted, it presents its bill. The Artemis II crew are, right now, in the first days and weeks of that waiting period. The mission is complete. The data is being collected. The dosimeters have been read, And somewhere in the biological systems of 4 human beings who are now back on Earth, eating food and sleeping in beds and walking in sunlight and breathing unrecycled air, processes are underway. Repair mechanisms working against damage, immune systems assessing and responding, cardiovascular endothelium, either restoring itself to normal function or beginning a subtle progression toward the inflammatory state that the Apollo data suggests may be the long-term cardiovascular legacy of cislunar radiation exposure. We will not know the outcome for years, perhaps decades. Perhaps we will never know with certainty, because 4 people is not a sample size from which strong causal inferences can be drawn. And the confounders of subsequent life history will always provide alternative explanations for whatever health outcomes eventually emerge. But the Apollo signal is there, and the physics is there, and the biology is there, and the combination of those 3 things, a preliminary epidemiological signal, a well-characterized physical mechanism, and a biological pathway connecting mechanism to outcome, is precisely the combination that, in any other domain of public health, would trigger a level of precautionary communication and risk disclosure that the current public presentation of crewed deep space missions does not approach. If a pharmaceutical company had a drug that produced a preliminary cardiovascular mortality signal 4 to 5 times the control rate, in a small but specific subpopulation with a clear mechanistic explanation connecting the drug's action to the observed outcome, the regulatory conversation would not be conducted quietly in the supplementary materials of academic papers. It would be conducted publicly, with the full weight of disclosure requirements designed precisely for this kind of preliminary but concerning signal. Space agencies are not pharmaceutical companies. The regulatory frameworks are different. The ethical structures are different. The nature of the enterprise is different in ways that matter. But the underlying moral logic, that people who are asked to accept a risk deserve to understand that risk with the fullest available vocabulary, including the parts of the vocabulary that are uncertain, preliminary, and uncomfortable, does not change because the context changes. It does not change because the mission is inspiring. It does not change because the alternative to accepting the risk is not going at all. And not going has its own costs: scientific, strategic, civilizational. It does not change because the people accepting the risk are volunteers. Because voluntariness is only meaningful when it is genuinely informed. And informed consent, in the full ethical sense, requires not just the disclosure of known risks, but the honest acknowledgement of the boundaries of what is known. The stars that made you did not ask your permission. The calcium in your bones did not choose to be forged in stellar nucleosynthesis, did not consent to being dispersed in a supernova, did not volunteer to spend billions of years drifting through the interstellar medium before being incorporated into a planet and eventually into a living organism. The universe assembled you from its own material without consultation. But you are not the universe. You are a conscious entity that the universe accidentally produced, or deliberately, depending on the philosophical framework you carry into that question. And consciousness changes the moral landscape of risk entirely. Consciousness means you can ask the question. Consciousness means you can demand the answer. Consciousness means that the gap between what the instruments know and what the broadcast shows is not merely an information asymmetry, but an ethical condition, a state of affairs that consciousness, applied rigorously, is obligated to examine and to challenge. The Artemis II crew looked out of porthole windows at a universe made of the same atoms that compose them. They floated in a capsule threaded through with radiation from stellar explosions that occurred before the Earth existed. They carried in their bodies the chemical legacy of stars whose light left them billions of years before the first human eye existed to see it. And they came home to a press conference where the questions were about the view. The view was extraordinary. The view was, by all accounts, indescribable in the way that only genuine transcendence ever is. The kind of beauty that arrives with such force and at such scale that the visual cortex struggles to process it as information rather than as revelation. The curvature of the Earth, the absolute black of space, the moon, seen not as a disk in a sky, but as a world hanging in a void, gray and pocked and ancient and real in a way that no photograph or simulation has ever fully transmitted. The view was worth talking about. The view was worth celebrating. But the view was not all that happened. And a species that contents itself with the view, that accepts the edited highlight of its own most dangerous and magnificent achievements without demanding the full account, is a species that is not yet entirely serious about the journey it is attempting to begin. We are attempting to become an interplanetary species. We are attempting to extend the reach of biology, of consciousness, of the particular kind of self-awareness that looks up at the night sky and feels something it cannot name, beyond the single world that produced it. That is an ambition so large, so consequential, so unprecedented in the 4-billion-year history of life on this planet, that it deserves to be pursued with the full seriousness it commands. Full seriousness means full vocabulary. Full vocabulary means the instruments and the broadcast, the dosimeters and the highlight reel, the cardiovascular signal and the triumphant splash down, the architecture of forgetting and the architecture of the rocket. All of it held together, without editorial selection, without the institutional preference for the parts that photograph well. Because the stars that made you did not edit their own deaths to spare you the difficulty. They exploded with everything they had, scattering everything they were into the dark, and trusted the physics to do the rest. We could afford to be at least that honest. There is a concept in evolutionary biology called the bottleneck, a moment in the history of a species when its population is reduced to a small number of individuals, passing through a narrow genetic aperture that determines everything that comes after. The survivors carry forward only a fraction of the genetic diversity that existed before. What makes it through the bottleneck shapes the species for generations, sometimes permanently, sometimes in ways that only become visible millions of years later when the lineage has diversified enough for the original compression to be readable in the genomic record. We are, right now, at a different kind of bottleneck. Not genetic, civilizational. The decisions being made in this decade about how to pursue human deep space exploration, about what risks to disclose and what risks to absorb in silence, about how honestly to account for the biological cost of the ambitions we are pursuing, will determine the shape of everything that follows, not because this decade will produce the definitive answers, but because the frameworks established now, the ethical architectures built now, the precedents set now about what counts as adequate risk disclosure and what counts as acceptable institutional silence, will calcify into the norms that govern human spaceflight for the generations that come after. Norms are harder to dismantle than rockets. Rockets can be redesigned in years. Institutional norms, once established, persist for decades, embedded in regulatory frameworks, in organizational culture, in the unspoken professional consensus about what is appropriate to say and what is appropriate to leave unsaid. The norms being built now around the Artemis program and its successors will be the norms inside which the people who attempt to reach Mars will operate. And the people who attempt to reach Mars deserve norms built on honesty, not on the institutional preference for comfortable narratives. This is not an abstract concern. It is a concern with a specific history, a history that space exploration shares with every other domain of human activity, where organizations have managed the tension between institutional confidence and scientific uncertainty in ways that eventually produced catastrophic failures. On January 28, 1986, the Space Shuttle Challenger broke apart 73 seconds after launch, killing all 7 crew members. The technical cause was the failure of an O-ring seal in one of the solid rocket boosters, allowing hot combustion gases to escape and trigger the structural breakup of the vehicle. But the deeper cause, the cause identified by the Rogers Commission investigation that followed, was a failure of organizational culture. Engineers at Morton Thiokol had raised concerns about O-ring performance in cold temperatures. Those concerns had been communicated upward through the management structure, and somewhere in the gap between the engineer's data and the launch director's decision, the signal was lost, absorbed into an organizational culture that had, through years of successful launches despite known technical anomalies, developed a normalized tolerance for risk that was never adequately formalized, never adequately scrutinized, never adequately exposed to the kind of external challenge that might have forced a clearer accounting of what the data actually said. The O-rings were not a secret. The cold temperature concern was not classified. The information that could have prevented the loss of 7 lives was present in the system. It simply failed to travel with sufficient urgency and sufficient clarity from the people who understood what it meant to the people with the authority to act on it. 17 years later, on February 1st, 2003, the Space Shuttle Columbia disintegrated during re-entry, killing all 7 crew members. The technical cause was damage to the thermal protection system on the wing's leading edge, caused by foam insulation shed from the external tank during launch. The deeper cause was, again, organizational. Engineers had again raised concerns about the severity of the foam strike, about the possibility of catastrophic re-entry heating through the damaged tiles. Those concerns had again traveled upward through a management culture that had, again, developed a normalized tolerance for foam shedding because previous missions had survived it. The possibility that this time was different, that the damage this time exceeded the threshold beyond which previous survivals were no longer predictive, was not given the institutional weight it deserved. The physicist Richard Feynman, serving on the Rogers Commission after Challenger, made an observation that has resonated across the subsequent decades of spaceflight history with the force of a physical law. For a successful technology, reality must take precedence over public relations. For nature cannot be fooled. Nature cannot be fooled. The O-ring does not care about the launch schedule. The thermal protection tiles do not care about the public affairs calendar. The Van Allen belts do not adjust their proton flux in deference to the broadcast window. The galactic cosmic rays threading through the Orion capsule during the Artemis II transit did not pause their ionization of cellular DNA because the camera was showing something more photogenic through the window. Reality operates independently of the narrative constructed around it, and the gap between reality and narrative, the gap that institutional communication consistently manages in the direction of the narrative rather than the reality, is precisely the gap in which Challenger was lost, in which Columbia was lost, and in which, if the lessons of those losses are not applied with sufficient rigor to the new domain of deep space human exploration, future crews may be lost in ways that are more difficult to investigate because they unfold not in 73 seconds of catastrophic structural failure, but in the slow, quiet, decades-long biological consequences of accumulated radiation exposure and physiological remodeling that was known, measured, documented, and insufficiently communicated. The difference between the shuttle disasters and the radiation question is temporal. The shuttle disasters announced themselves immediately, with the finality of explosion and disintegration, in a form that forced accountability, that created a visible gap between the institutional narrative of acceptable risk and the physical reality of catastrophic failure that was impossible to deny or defer. The biological consequences of deep space radiation exposure do not announce themselves this way. They arrive slowly, in the private medical records of former astronauts, in the statistical patterns of longitudinal health studies, in the cardiovascular mortality data of a small cohort of men who flew to the moon 50 years ago and have been dying at elevated rates from heart disease ever since. There is no explosion. There is no commission. There is no moment of undeniable, public, photographic evidence of the gap between what was said and what was real. There is only the slow accumulation of data in scientific journals and the slow accumulation of biological damage in the bodies of the people the data describes, and the slow, patient work of researchers who have dedicated careers to characterizing a risk that the institutions responsible for managing it have systematic incentives to present as smaller than the data suggests. This is the most dangerous kind of institutional failure, not the catastrophic kind that produces its own correction, but the chronic kind that proceeds without forcing the accountability that would arrest it. The kind that can persist for decades, absorbing its costs quietly, expressing them in ways that are always deniable, always attributable to confounders, always separated from their cause by enough time and complexity to make the causal argument difficult to prosecute with the certainty that public acknowledgement seems to require. And yet the physics does not require that certainty. The biology does not require that certainty. The ethics of risk disclosure does not require that every uncertainty be resolved before disclosure occurs. It requires the opposite. It requires that uncertainty itself be disclosed, because uncertainty is information. And information withheld from the people bearing the risk is information weaponized against them. However unintentionally, however structurally, however deeply embedded in an institutional culture that genuinely believes it is managing the risk responsibly. Consider what responsible management of this risk would look like in practice. It would look like mission briefings that include, alongside the trajectory graphics and the life support specifications and the re-entry parameters, a clear and detailed account of the radiation environment the crew will traverse. Not in the sanitized language of acceptable dose limits, but in the biological language of what those doses mean for the specific tissues and organ systems most sensitive to the radiation types the mission will encounter, with the uncertainty ranges made explicit rather than collapsed into a single point estimate that implies a precision the data does not support. It would look like longitudinal health monitoring programs with timelines adequate to the temporal profile of the risks being monitored. Not 5-year follow-up studies for risks that may express themselves over 30 years, but lifetime commitments to the people who carry the biological legacy of these missions in their bodies for the rest of their lives. It would look like public communication that does not reserve the complexity for the peer-reviewed literature and offer the simplicity to the broadcast audience, as though the public were incapable of holding complexity, as though the wonder of space exploration were incompatible with the honest acknowledgement of its costs, as though the people watching the launch from their living rooms had not already demonstrated by watching that they can hold inspiration and gravity in the same moment. It would look like the full story. Not because the full story is discouraging. It is not. The full story of what human beings are attempting in space is more inspiring, more profound, more genuinely moving than the edited version. Because the edited version is the story of a rocket and a successful splashdown. The full story is the story of a species that evolved on a single planet, under the protection of a magnetic field it did not know existed until the 20th century, that has now sent its members beyond that protection into an environment of lethal complexity, carrying instruments sensitive enough to measure the damage being done to them in real time, and has chosen, despite the fear, despite the uncertainty, despite the wide error bars and the cardiovascular signal and the neurological implications and the irreducible unknowns, to go anyway. That is not the story of naive optimism or institutional overconfidence. That is the story of conscious, informed, eyes-open courage. Or it could be, if the eyes were actually open, if the information were actually complete, if the courage were actually built on the foundation of full knowledge rather than on the more comfortable foundation of selective presentation. There is a species of courage that does not require the full picture. It is the courage of momentum, of institutional confidence, of the trained professional who trusts the system because the system has delivered success before. That courage is real. It produced Apollo. It produced the ISS. It produced Artemis. It has carried human beings to extraordinary places and brought most of them home safely. But there is another species of courage. Rarer, harder to cultivate, requiring something of the institutions that enable it as well as of the individuals who embody it. That insists on the full picture before stepping forward. That demands the wide error bars alongside the point estimate. That reads the supplementary materials. That asks what the dosimeter said, not just what the camera showed. That holds the inspiration and the complexity simultaneously, without resolving the tension between them into the simpler narrative of pure triumph. That is the courage that the next phase of human space exploration requires, not because the destinations are more dangerous than what came before, though they are, but because the consequences of proceeding without it, at the scale and duration of what comes next, in the radiation environment of interplanetary space on a 6-month transit to Mars, are not reversible. You cannot bring a crew back from the midpoint of a Mars transit because the accumulated radiation dose has